Okay, thank you very much, Anita. Before I speak, I'd like to say a few words. Wo hen gao tsing lai dao mei li de Hangzhou. I'll wait for the interpreters to translate that into Chinese. CC. Thank you very much to the director, to John Liu, the organizer, the wonderful organizer, to the colorful Dominique Cardon, of course, and everybody else over here. Thank you for listening up. I'm going to talk about my favorite subject, which is purple. You've heard about plant dyes and insects, but I believe that those in the East should know Western history, and those living in the West should also know Eastern history. So take it as a kind of a historical session with some archaeology and some chemistry, but don't be afraid. I basically wear two hats. I'm the director of a center, Edelstein Center, that analyzes ancient artifacts, but mostly the colors, dyes and pigments. And also I'm a faculty member in the Department of Chemical Engineering, but don't be frightened. There'll be a little bit of chemistry on the need-to-know basis, as we say. And I'm privileged to be in a very interesting college of its combined engineering, design, and art. It has the best of all the worlds. Okay. As far as that, it's interesting that when we talk about the Near East and the Far East, it's a funny name, because to the Europeans, you guys living here is the Far East, and those in the Middle East is known as the Near East. I imagine if you're living in Asia, this would be the Near East to you, or the Near West, and everybody in the Near East would be the Far West, or something like that. Anyway, it was a nice flight coming over to first Hong Kong, and then my way up to Hangzhou, which was very nice to be here. Now, when I mentioned the name, when I use the name, and I've used it in a number of talks that I've given in the past, purple, the dye of dyes. It's a nice poetic form. It is the most spectacular, magnificent, royal, imperial, you name it, holy dye that is possible, the dye of dyes. And I thought I was clever enough to be the first one to use that particular expression. But woe unto me, I'm not the first one to have used it. The dye of dyes is mentioned in the following poem. Who has not heard how Tyrian shells enclose the blue, that dye of dyes, whereof one drop worked miracles, and colored like Astarte's eyes? Raw silk the merchant sells? Which poet wrote it? This gentleman, 150 years ago, Robert Browning, wrote the dye of dyes in one of his poems, popularity poem. He wrote it in the volume known as Men and Women. He mentioned dye of dyes, and interestingly, throughout that poem, he talks about the wonderful blue, not purple. To him, blue was the new purple. Anyway, as we know, the dyeing craft is an amazing craft. It's a craft to die for. I'd love to hear the Chinese translation of that. A craft to die for. Hi there. The ancient dyer, as Richard has spoken before, and John Liu also, the ancient dyer was an advanced chemist. Without going to all the chemical principles, modern chemical principles, that the primitive dyer used, he or she was an advanced chemist. Many wonderful chemical principles that I won't go into in detail, although one can do that. We analyze the ancient dyes, as Richard has done and John Liu has done. I call it microscale archaeological chemistry. We do a lot of extractions, a lot of analyses, and the workhorse is HPLC, high performance liquid chromatography. We have in the regular HPLC, a classical one. We also have an ultra HPLC from Waters to do the analyses, which is very nice, and it gives us a lot of interesting information. For example, the purple pigment that you see here from a snail, it can be divided up into 10 different components. That was my chromatogram, by the way, Dominique. It can be divided up into 10 different components. What you see here as a purple color, the eyes can be beautiful, but the eyes are not the best detector of color. They cannot do a separation of the various colorants. And in the purple color that you see, there are yellows, isotenoids, yellows and yellow-orange. There's the blue, of course, indigo, and there's reds and violets, etc. So altogether, we get this purple color, but the HPLC can separate out for you. It can give you what is known as a retention time. Each peak, for those of you unfamiliar, each peak comes out at a certain time, retention time it's called, but it also gives you a spectrometric property besides chromatographic property, such as the UV-Vis absorption spectrum, and you could tell the difference between the various dyes with these two characteristics, both the retention time and the spectrum. Okay, in short, we can identify the various components. Now, in the beginning of dye analyses, as Pfister, one of the main founders of dye analyses, you needed large quantities, chemical reagents that you used. It was interesting to see, Richard, the sample that you got from the museum, a big chunk. But today, we can also do the analyses on what I call micro-destructive analyses. Not even micro, I call it nano-destructive tests, that if you see the sample with a magnifying glass, it's more than enough. And we have done analyses not on a thread, but on a single fiber from a thread. A single fiber from a thread, which is to the naked eye invisible, you can't see it, but under the microscope, you can see it and you can still get enough. So much so that when you look at this particular world, and we'll talk about that very shortly. As far as archaeological sites are concerned, now if you take a look at I've done a lot of work in the Middle East, specifically Israel, Egypt, etc., in that area. If you take a look at the map of Israel in the Judean desert, as Richard has spoken before, it's a dry area, and the Judean desert, as being a desert, arid area, you get a lot of various organic components like baskets, sandals, and of course, fortunately, textiles. This is the same area as the Qumran, the famous Dead Sea Scrolls, Masada, some of you might have heard of, might have actually been there, etc. These are various sites, Qumran, Masada, beautiful and famous international sites in Israel. Now, as also you heard, there are basically two main types of dyestuff sources. There's flora and fauna. There are plants and insects and sea snails. My favorite is not, I've done analyses on plants, I've done analyses on insects, but the most challenging is the dyes from sea snails, the pigments from sea snails, because that was the most difficult technological process in the ancient world and even as we speak today. Now, Prince. Thank you, Prince. We're not talking about purple rain, but the purple pigment. Okay, rest in peace. You did great work. Purple rain, we're talking about the various snails that we used for producing the purple pigment. These are the three most famous snails. They're called murex, is a popular name. The Darius, Trunculus, Hemistoma, they've undergone different names, etc. You could see the first one, the Darius, the sharp spikes, the truncated spikes, the trunculate, and the red mouth, the hemistoma, the beautiful one. From the living snail, you can get these particular pigments, and they were not only used for kings and royalty, it's also known as royal purple, imperial purple, also for the vestments that are described in the Bible for the high priest. These are known as royal purple, or in Hebrew, Argaman, and also there's a biblical blue, which is known as Tekhelet. It's a bluish purple, which we'll talk about that in a second. How did they obtain those? Well, you first have to go diving for snails. When you go diving for snails, we go to the Mediterranean, a certain area in the Mediterranean, way up north. This happens to be in Israel. We get a nice basket full of snails. One of the snails I see is asking for help because he's going to know what's going to happen to him. When you do the dye extraction, you have to hit the shell, expose the gland. It is known as the hypobranchial gland. Don't ask me what it does. I have no idea. But I know how to say it, hypobranchial gland. Inside the gland, there is no color. There is no pigment over there. It's mucousy, it's barely white, like saliva, like spit. But once you cut it open, take a look what happens spontaneously in the laboratory. The white turns yellow, slowly, slowly. Some of it times it turns greenish, sometimes bluish, and to the final purple color. If you do it in the laboratory with the, obviously you don't have sunlight, it can take about half an hour, 45 minutes, up to an hour for the final color to develop. If you do it out in the hot Mediterranean sun, it could be a matter of 3 to 5 minutes where you get the final purple pigment produced. Now, what do you do with that? As I said, you can have different components over there. The main components, even though there are about 10 different components, as I said, but the main components are known as indigoids. They have the indigo skeleton. You see the indigo skeleton of the molecule. Indigo, as we know, not only from plants, but also from sea snails, indigo is bluish. And there's also monobromo indigo, indigo with 1 bromine atom, and there's dibromo indigo, indigo with 2 bromine atoms. The dibromo indigo is a reddish purple, indigo, of course, bluish, and monobromo indigo is somewhere in between. It's not a mixture, it's its own component, but its color is a kind of a violet color. Those are the 3 main components that you have. Now, we have seen purple as a paint pigment. We're talking about textiles for dye, but purple as a paint pigment, there's one beautiful example of that. That purple pigment was used as painting, and it belongs to King Darius the Great. They're always known as King such and such the Great. There was never the King so-so. King Darius the First, or the Great, who lived from 521 to 486 about. This is a stone sculpture in Iran. And we're fortunate to have in the Bible Lands Museum in Jerusalem a vase, a stone jar. It's marble jar. You can see the dimensions of it here. It's about 37 centimeters high. And it is dated to 486 BCE. How do we know that? Well, this is part of it. One half survives. The other half is not in great shape. I call it a Persian Rosetta Stone. Historically, it's interesting. Why Persian Rosetta Stone plus, 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 plus? Because it's got 4 different languages on it. The Rosetta Stone in the British Museum, we all know, has 3 languages. And this one has 3 cuneiform inscriptions, Old Persian, Elamite, Akkadian, plus Egyptian hieroglyphics. And you can see, by the way, the cartouche, an oval shape around a very important name, decorating it. That's when you go to the museums and you look at Egyptian hieroglyphics, the cartouche, the oval shape, is where the king's name appears. So it says King of Upper and Lower Egypt, Lord of the 2 lands, Darius, or in ancient Farsi, Daryavaush, living eternally, year 36. It says it all there in Egyptian hieroglyphics as it was translated. And what's funny, living eternally, year 36, that's when he died. And the year 36 is about 486 BCE. Oh well. So wishful thinking. But this is a beautiful marble jar, and if you look very carefully, you can see purple residues all over. When I analyzed it, just with a magnifying glass all over, what was amazing is that even the bottom, the base of the marble jar, you could see residual purple pigment, which is rubbed off. In other words, try to extrapolate. This entire marble jar was painted purple. The whole thing. There's no reason to paint the bottom of it also purple. It was not a dyeing vessel, and it did not contain any purple inside. It was just a magnificent objet d'art, a work of art that was probably given by the King Darius to those that he held in high esteem, as opposed to presents to Darius, but we can discuss that further. Anyway, when I took a look at the chromatogram, when I analyzed it, lo and behold, of course, it's reddish purple, so you're going to see a lot of dibromo indigo, the reddish purple. There is some violet monobromo indigo, a tiny bit of indigo, an insignificant yellow component. A ton of dibromo indigo. Obviously, it comes from a mollusk. But when I analyzed it, it troubled me that I didn't know which of the 3 species was used. We call this provenance studies. In archaeology, they do a lot of what is known as provenance. They look at a metal, for example, a sword. They do elemental analyses, and they say, it came from this region. Or they look at a clay vessel, a pottery, they analyze the various elements inside it, and they say, it came from this earth or that earth from different parts of the world. I call it biological provenance. Which of the 3 species was used to produce that particular purple pigment? So what is the Molluskn source for this? When I analyzed a whole bunch of different snails from the Eastern Mediterranean, and I took a look at archaeological samples. I looked at the trunculus, the brandaris, the hemistoma, and these are the different components that I got, and here it comes. The various, okay, easy, tiger. Okay, all right. It's jumping like crazy, it's not supposed to be. Anyway, the various components over here, it is not supposed to jump like this. 1 second. Okay, and then I'll do the effect again. Basically, the various yellows, when I looked at the various snails, I noticed that the Darius pigment, as well as trunculus pigments, have a significant presence of monobromo indigo, whereas the brandaris and the hemistoma, and also the one from the Atlantic when I analyzed afterwards in La Rochelle and other areas, the monobromo indigo is insignificant, very small quantity, if at all. In other words, the key, as I wrote over here, the key to identifying the source of a pigment is if you see a significant amount of monobromo indigo. I also quantified it in one of my publications. If you see a significant amount of monobromo indigo, it can only come from a trunculus species. So that is the key to all of this. Okay, now let's see. Let's continue with this effect. Okay, which means that let's take a look at around the world, the ones that I analyzed and others, like Jan Wuter and Yanis from Greece and others. Every single archaeological pigment that's been analyzed, archaeological purple pigment that's been analyzed, has a significant amount of purple pigment, whether it's from what is now Israel, what was in Phoenicia, what is in Greece. Every single one has monobromo indigo, which means that we know, since monobromo indigo cannot be produced artificially by natural means, it is an integral part of the purple pigment, that it comes from the trunculus species. In other words, up until now, to date, unless you prove me wrong, all archaeological purples were produced from the Hexaplex trunculus species. Now, is it possible that other pigments from other snails might have been added? It's possible, as we'll see very shortly. But the trunculus species was used throughout. And when I analyzed it, it turns out that there is a difference between these 3 species. More than that, the Hexaplex trunculus is different from the other snails. The brandaris, hemistoma, and others have mainly dibromo indigo. When you analyze, of course, you'll see some other components, but the main component is a reddish purple dibromo indigo. However, the trunculus species has, besides monobromo indigo, I have found that there are 2 different varieties of trunculus species. I'm about to call them subspecies, but I'm not a zoologist. When I had a talk with Andre Verhecken, who knows a lot about zoology, he said, I may not be able to call it subspecies because it has a certain zoological definition. But for us right now, let's call it subspecies. There are two types of trunculus snails, which the literature only discusses a kind of a blue perhaps from it, but no. There is a trunculus variety, as you can see from the slide, that gives you a reddish purple pigment, and there's one variety that gives you a bluish purple pigment. The reddish purple one is rich in dibromo indigo, and the bluish purple is rich in indigo pigment. It has all three, but one of them has a lot of indigo, the other one has a lot of dibromo indigo, and these were used. So, if we look back at the If we look back at the Darius pigment, we see that there's a lot of dibromo indigo, a significant amount of monobromo indigo, indicating that it comes from a trunculus, and this pigment was produced from a dibromo indigo rich murex trunculus or hexaplex trunculus. That's purple as a pigment. It's a unique kind of sample, because the ones that you may have read about, Terra in Akrotiri, the saffron gatherers, so in the saffron there is some purple pigment. But this is a jar where the whole thing was painted with purple pigment from snails. Now purple is a textile dye. Purple is a textile dye. As we look at it, we have various Phoenician purple dyeing vats dated to more than 3,000 years ago, some of them. They're now in what is known as ancient Israel, but they've been found other places. Phoenicia being the modern Lebanon today. From Kabri, 7th century, to Shikmona, 9th century. You could see the curvature, you can extrapolate on it. You could see the curvature, and you could see the purple pigment all the way to almost to the very top of this particular potsherd, which was part of a clay vessel, a clay vat. Okay, when I took a look at this and I did a natural dyeing, when I did it at the same year, Inga, Baskin-Canold also did that in France. I did it, and before that, John Edmonds of blessed memory did that also previously, a couple of years before that. When we looked at the dyeing process, an all-natural dyeing process, we're trying to understand how it's being done and what is involved in it. You basically produce the pigment, the solid pigment, which is dibromo indigo, monobromo indigo, whatever. It's water insoluble. You have to dissolve it like indigo, the indigo dye. You have to dissolve it in a form that you can do the dyeing. You have to reduce it. When you reduce it in the presence of an alkaline solution, the alkaline solution is brought about by Pliny's salt. Pliny, I had a discussion on it, that Pliny was correct in his old description of the purple dyeing process. He talked about a salt. Now salt, as we know when we teach general chemistry, there are neutral salts, like table salt, sodium chloride, won't change the pH, but there are also acidic salts, and there are basic salts. So if you take sodium carbonate, which is a natural salt, you produce an alkaline solution, and it's an ionic form. The dye is soluble. You get the greenish dye. When you take sheep, okay, you shear the sheep, you wash it, etc., and you have a nice amount of sheep. You put the wool, you take the wool in the soluble dye, you get the green solution. Look what happens when you raise it up in the air. It undergoes oxidation from a greenish color, slowly, 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 to your purple color. Undergo air oxidation. And the reducing agent for all of this is the bacteria that's in the glands. In other words, the process is so complicated because it's simple. It's a built-in process. All you have to do is just put in an alkaline salt. That's all. The reducing agent, it's in there. It's the bacteria. And you have to have the glands in there, the meat. So the bacteria lives off and reproduces from the meat. That's the nourishment, that's the food. More bacteria, more reducing agents, more molecules can undergo reduction, and therefore you have this complicated, simple process. As we've done it, this is the pigment, the reddish purple pigment distributed throughout. You could do this is the fermentation, the greenish solution. When you raise it up in the air, it undergoes oxidation from green to eventually purple before your very eyes, which is wonderful. Just like indigo, it's in indigoid, so the overall process is similar to dyeing with indigo. Now, one of the insights that we got when I did the analyses together with Chris Verhecken from Antwerp, a 1500-year-old polychromic textile, which is beautiful, late Roman period. Now, we analyzed some of these purples. Okay, the yellows are interesting, the reds are interesting, but I wanted to look at the reddish purple and the bluish purple, etc., and some of the turquoise. So there was the turquoise sample under the microscope, and lo and behold, there's indigo. Wow, there's indigo. So it is a plant-based, probably woad, but it could be Indigofera, etc. You can't tell the difference between them. Sometimes there's indirubin, sometimes not, whatever. Okay, that was okay, but not the most interesting. When we took a look at the reddish purple pigment, a very small sample of it under the microscope, you could see nice uniform color. And when we took a look at the chromatogram, lo and behold, again, we saw a lot of monobromo indigo, a lot of dibromo indigo, so it's a reddish purple. It makes sense, obviously. They work like paints when you mix them together. And when you look at the blue purple, we were very surprised to find the following. The blue purple had a lot of indigo and a significant amount of monobromo indigo, a bit of dibromo indigo. Now, again, the presence of indigo, if I were in a scientific court of law and somebody would ask me, was that indigo introduced from a plant source? Your Honor, I don't know. Chances are no, there would be no point. But it could come from a plant source also. We're assuming that it all came from a mollusk because the sea snails have these pigments in them also. And what was amazing, when I looked under the microscope, I looked at some of the yarns, and take a look. You can see it, I think, pretty clearly from where you are, one of those slides. You can see that the yarn is really made up of 3 different colors. There's a yellowish thread that's undyed. There's reddish fibers, and there's bluish fibers. In order to do an analysis on that, you had to dissect it, and this took a whole day without breathing under the microscope, because if you breathe, everything goes. So with tweezers under a spherical microscope, this was extremely difficult to do. We were able to separate out the various fibers from this particular thread and analyze, this was crazy, analyze each of the fibers, and this is what we got. When you looked at the reddish only fibers in there, we got the indigo, the monobromo, the dibromo indigo, etc. The bluish only fibers, you get a lot of indigo, some monobromo indigo, and a bit of dibromo indigo. When you look at it's not composition per se, but these are peak areas. You can think of them as compositions. What we saw is that in all of them, there's a significant amount of monobromo indigo, as opposed to the Brandaris hemostoma, where there's virtually no monobromo indigo. So they're all produced from trunculus snails. But but as to what is the source of these particular purple pigments that we got, well, when we took a look at the fibers that were only reddish purple and homogeneously colored, there was only one fleece that was spun together to give you these yarns, and it was with a dibromo indigo rich trunculus because of the monobromo indigo, rich in dibromo indigo, plus maybe there's another snail that was used, but let's hold off with that. The blue-purple yarn, which we dissected into 3 different fibers, some of them were reddish-purple, and some of them were more blue-purple, and some of them were yellowed but undyed. 3 different fleeces were spun together in order to get you these yarns. And what does that mean? The yellow, as I said, was undyed. The red-purple is because a dibromo-indigo-rich trunculus was used, and the blue-purple was an indigo-rich trunculus. Now, what's interesting is that in the blue-purple yarn, the red-purple ones are less red than the red-purple that you see up on top. In other words, what is very possible is that in order to get red-purple, a dibromo-indigo-rich trunculus was used and added to it Brandaris or hemostoma. In other words, trunculus was always used. Was a Brandaris and or hemostoma also added to it? It's possible. And this is how they obtain even redder purples than the red-producing trunculus would give you. As far as the royal purple or Argaman is concerned, the biblical Argaman royal purple for the high priest, Aaron the high priest, let's take a look at the Judean desert site in Masada, where a number of real purple textiles were found. And some of you might have heard of King Herod about 2,000 years ago. King Herod reigned in Judea from 40 BC to about 4 BC. King Herod's in Masada, there is a throne room. You could see these 4 notches on the floor, and this presumably is where a canopy was, where the king would meet the guests, the dignitaries that would come to him. Anyway, there are coins of King Herod. There's no image of King Herod, but there are various coins, Herodoi Basilios, I hope I'm pronouncing it correctly, in Greek of King Herod. A few little fragments that were found. When we analyzed it, this is what was found. A lot of dibromo indigo, when you do the integration of it, this is what happens. You get a lot of dibromo indigo, a nice amount of monobromo indigo, again a trunculus, but a dibromo indigo rich trunculus was used for producing this particular snail. This is a royal purple. This picture, again, what you see in pictures, there's Photoshop, etc. This is highly magnified. It's not Photoshopped, but it's under a bright microscope light, so it gives you a pinker look than the one that you saw before. Anyway, this is a royal purple color. Now, as far as biblical blue is concerned, as far as biblical blue is concerned, which is known as Tekhelet, some of you might have heard of it, it's a bluish. Now, when we analyzed the textile, what we saw was, lo and behold, the first time a textile like this was found, an archaeological textile, was found from ancient Israel up in Masada. It has a lot of indigo, of course, monobromo indigo, and some dibromo indigo. This was produced, and you can see the pigment produced from this particular snail. It's an indigo-rich trunculus. Again, my thesis is there are 2 varieties, 2 subspecies of trunculus. One gives you reddish purple, one gives you a bluish purple, depending on how much dibromo indigo is there, depending on how much indigo is there. In order to analyze this and to give this in a historical framework, let's take a look at the Talmud, the Jewish Talmud. It was written the first 500 years. It's a multi-volume work that discusses Jewish laws and also describes the various crafts that were available at the time. You can learn a lot about what existed in the Roman period. And take a look, there was a Rabbi Meir, the late 2nd century, 1800 years ago. This Rabbi Meir described in a very poetic sense the bluish nature of Tekhelet. And take a look at what he says about this Tekhelet. Why is Tekhelet different from all the other colors? Because Tekhelet resembles the color of the sea, and the sea resembles the sky, and the heavenly skies to the divine throne. As the prophet Ezekiel stated in his vision, through the firmament I saw the divine throne appearing how? As the color of the sapphire stone. Now, sapphire stone, even though sapphire sounds like sapphire, it's not sapphire. Take a look at this archaeological sample, first black and white, and you can see the color developing on it, just to tease you a little bit. You can hum along if you want. This to me is one of the most beautiful of colors. A dark blue purple or blue violet. And what is it? It's the color of the sapphire stone. In ancient times, the sapphire stone is the blue stone, otherwise known as lapis lazuli, my favorite stone. That is the sapphire stone, etc. That's the color of Tekhelet, as I said. So to summarize, there's two varieties of trunculus. Trunculus was always used to date for all archaeological dyings, no matter what you read in the literature about the Darius used for royal purple. I disagree with that. All archaeological samples that were analyzed have monobromo indigo in it, and it can only come from a trunculus in a natural way. Possibly, Darius and hemistoma might have been added to the red one to give you a redder, even a redder, but you could see two archaeological samples, both of them from Masada, both of them about 2,000 years old. Summary. Okay, all Molluskn archaeological purples were produced from Hexaplex trunculus sea snail species, as I said. Every single one, until you find one that has no monobromo indigo, and then call me up. Some of the trunculus subspecies give reddish purple pigments, and it will give you reddish purple dyings. Others have bluish purple or violet, which will give you that kind of bluish purple dyeing. Now, how did the ancients know how to separate them out? In the little bit of work that I've done with Inga, you could tell them apart based on size, gender, male and female. I've seen geographical regional differences from north of Israel, for example, to more central Israel, etc. But I haven't done a statistical study. It's nearly impossible to annihilate all snails that you come in contact with in order to do a statistical study. Of course, these two types could have been mixed to obtain some in-between color if the dyer was not interested in a very specific kind of color. And other purples might have been added to it, as I said. And Pliny's description of the purple dyeing process was correct. So please don't say anything nasty about Pliny the Elder. He was correct. If you want to know more about archaeology of this stuff, I gave a talk at the ASOR, American Schools of Oriental Research Conference, about 5 years ago. It's on YouTube. And also, I gave a TED talk about a year ago, should you kiss with lipstick? To all those who are interested in kisses, I don't know. Should you kiss with lipstick? I will not tell you anything more. Look it up, TED Talk, my name. That's all, folks. Thank you for CC. Thank you.